Hi, my name is Katrine, and I would like to present this work called Private Aggregation with Application to Distributed Optimization. I will start by giving an introduction to the problem, and then I will introduce a few cryptographic primitives. Thereafter, I will present our private aggregation scheme, which will be followed by some simulations that illustrates its efficiency. In the end, I will give a few notes on the future work. In this work, we are considering multi-agent systems, such as the one depicted here. That is, we have a number of nodes, and they are connected by some communication network. We assume that each node holds some data, and that we would like to perform some computation on the combined dataset. We don't assume that we have a central unit that can collect all of the data and perform the computations. Thus, we would like to perform the computations distributed among the nodes. For this, there already exists a lot of distributed algorithms that can solve various problems. And what we have noticed in these distributed algorithms is that many of them only use neighbor-to-neighbor communication. And also, in many of them, each node in the network doesn't need to learn the value of its neighbors. Rather, they need to learn the sum of their neighbors' values. And for this reason, we would like to propose a privacy-preserving aggregation scheme for computing this sum, such that none of the nodes in the network will have to actually reveal their private data to the other nodes. To be clear, I would like to state the problem formulation. So let this curly in C here be the index set of the neighbors to node C, which is some central node as depicted on the previous slide. Then let the term neighbor aggregate for node C be this YC, which is then the sum of Sj, where Sj is a private value belonging to node J, which is in the neighborhood of node C. Our objective is then to compute this neighbor aggregate for each node in the network while not revealing the individual terms in the sum. There already exist many privacy-preserving aggregation schemes, thus we would like to highlight our contribution. So, in contrast to many of the existing solutions, we do not assume that the neighbors of a node can communicate, which we have illustrated here by the lack of communication lines between the neighbors. Also, we have managed to put the most heavy part of the proposed solution into a preprocessing phase, which can take place at any time prior to the actual execution. So that means at the time where node C here would like to compute the aggregate, its neighbors only need to send one message to node C. Also, our proposed solution is resilient to node dropouts. So that means if one of the neighbors drops out after the preprocessing phase, then the remaining nodes doesn't need to compute the preprocessing phase over again. For this, we need a few cryptographic primitives. One is secret sharing and the other is public key encryption. And here I will just give a brief introduction to both of them. Secret sharing is, of course, about a secret S. And what we would like is to generate so-called shares of S in such a way that each share doesn't leak any information about S. In fact, you need to combine at least T of the shares to again recreate S. In this way, we can distribute the shares among a set of participants such that each participant doesn't gain information about S. There are many different schemes to generate these shares, and all we require from the secret sharing scheme is that addition of secrets can be computed directly on the shares. That is, if we have two secrets S and V, then we can compute the shares of S plus V by directly adding the shares of each secret. Also, we need an encryption scheme, and here we can use any public key encryption scheme. So each neighbor to node C generates a public key and a secret key. They of course keep the secret key to themselves, but they publishes the public key. So as you can see, each neighbor knows the public key of the other neighbors. And since these keys are public, then also node C is allowed to learn the public keys. We're now ready to explain the idea in our proposed method. And just to remind you, the goal is for node C to learn the sum of its neighbors' values. So in this case, S1 plus S2 plus S3. And what we propose is that each node mask their secret value by a random value that they choose themselves. So in this way, node C only learns this masked value here. So he doesn't get any information about the secret data. So the problem now is for node C to learn this big R value, which is the sum of the little r i's, because then he can use or he can subtract big R from the sum up here to learn the correct sum. And down here, we of course want node C to learn big R without learning any of the individual RIs, because in that case, we would again lose privacy. So it's actually the same problem we have. But the advantage now is that this problem doesn't depend on the secret data. So we can solve this problem prior to the actual computation. And this is how we have introduced the preprocessing phase. The preprocessing phase, the idea is to use the secret sharing scheme to generate shares of the big R value. That is, each neighbor generates shares of their chosen random value and distribute these shares to the other neighbors. However, since the neighbors cannot directly communicate, they encrypt the shares using the public key encryption scheme and then send to node C, who can forward. Each neighbor then generates their own share of the big R value by summing the received shares. And this equality here holds by the properties of the secret sharing scheme. At the execution time, each neighbor then sends their secret data masked by the random value along with their share of the big R value to node C. And node C can, from the received shares, recreate the big R value and use this to calculate the sum of the secret data of its neighbors. And this is, of course, without learning any of the individual secret data points. As I've already mentioned, this method is resilient to node dropouts. So that is, if node 2, for instance, drops out after the preprocessing phase, then as long as there's still T remaining nodes, the remaining nodes can carry on without having to do the preprocessing phase over again. And this is because node C will still be able to generate big R from the remaining shares of R. And this is again because of properties of the secret sharing scheme. Now, to improve efficiency, we note that each neighbor could choose a random vector of m random values instead of just a random scalar. This is, in a sense, a way to complete m preprocessing phases at once, which is relevant if the nodes are to complete m iterations of some distributed algorithm. The preprocessing phase will be the same, only now with vectors instead. Here in the end, I would like to illustrate the efficiency of the preprocessing phase. For this, we have done some simulations just on a laptop of the preprocessing phase. And here we have measured the execution time as a function of the number of neighbors to each node in the network. So as seen, when there are only few neighbors in the preprocessing phase is really fast. And as we increase the neighborhoods, we also have an increase in the execution time. However, interestingly enough, when we use our idea for improving the efficiency, which in a sense was to complete multiple preprocessing phases at once by each neighbor choosing m random values instead of a random scalar, then the execution time does not really increase, at least when the neighborhoods are small. For instance, for the blue curve here, we have 3 nodes in each neighborhood, and as you can see, the execution time is almost constant, no matter the size of m. For the future work, we would like to generalize the proposed scheme such that other functions than the neighborhood aggregate can be computed among neighbors in a network. Thank you very much for listening.